Great pleasure to be here. I'm going to be talking about research that's done both at McGill University as well as DeepMind on reinforcement learning agents. And just as a quick introduction, for those of you who maybe haven't heard of reinforcement learning, it's a way of learning from interaction with an environment that's inspired by animal learning theory and psychological theories. And so you have in the picture there a little mouse that's doing a reinforcement learning task. It's basically pressing a sequence of levers in order to get to its reward, which in this case is food. In automated agents, reinforcement learning proceeds roughly the same way, by the agent interacting with an environment, observing the state of that environment, and taking a sequence of actions and then receiving positive and negative rewards. And so the goal of the agent is formulated as maximizing the expected cumulative return that it would get over time. Now, perhaps the poster child application so far and big success of reinforcement learning has been this AlphaGo program, which was developed at DeepMind, which is the best Go player among people and computers. And it's a very clear application of reinforcement learning in the sense that you have a system that perceives the state of the board, plays the game by taking legal moves, and at the end of the game receives a reward which is +1 if it's lost, if it's won, and -1 if it's lost. And there's no other rewards along the way. So we formulate the task through this very distant signal that the system is receiving, and it's learning to optimize this by playing lots of games against itself and training from trial and error. So that's very exciting. It allows the system to invent new ways of playing superior to those that people know about. Some people are scared of this. I find it really, really exciting. But then the question is, are we done? And in some sense, as exciting as Go is, it is a somewhat limited application in the sense that it's a game, it's deterministic, it's perfectly observable, and does not have all the messiness of real world. So I don't know what you dream of when we talk about AI. I personally dream of cooking robots. And that's not just because this is a big chore in my family, also because I'm really bad at it. But also from the point of view of AI, it's actually a really interesting task because there's lots of things that go wrong. You need to troubleshoot as you go along. It's definitely partially observable. And you need to learn how to do it effectively from one stream of data and adapt to new situations. And so people don't even think that this is a hallmark of intelligence, right? We all kind of do this reasonably well. But for AI machines, it's actually a really complicated task. So what I want to really talk about is, can we actually use reinforcement learning not just to learn how to solve a problem, but actually to build the kind of knowledge that people use to solve cooking, okay? To build it in an automated agent through reinforcement learning means. And so to do this, I just want to revisit a little bit the kinds of knowledge that a reinforcement learning agent might have, and then sort of express some ways in which we could take these types of knowledge and learn them more flexibly in an AI agent. So if we look at AlphaGo, it really has inside of its brain two types of knowledge. One is what we would call procedural knowledge, how to play the game, and that's represented by a policy which has a deep network associated with it. This network looks at the board and outputs probabilities of different actions. And then the other kind of knowledge that we need is what we think of as predictive knowledge, okay? Predicting something about the state of the world. Now in AlphaGo, this is a very simple prediction. It just wants to predict whether it's going to win or lose the game. And this is the signal that's then used to train the policy network. So we have procedural knowledge and predictive knowledge. We would like to have our reinforcement learning agents acquiring these kinds of knowledge from data, but we would like to do this more flexibly rather than saying the agent has one policy and one value function. Perhaps an agent needs to learn about many different ways of behaving and needs to learn how to make many predictions about the world, right? Just like we do in everyday life. So I'm going to focus on these two types of knowledge. We're going to think of procedural knowledge as being represented through skills or goal-directed behavior. We're going to think of predictive or empirical knowledge as knowledge that predicts the effect of actions. And we're going to try and build these in a way that allows us to express many things in a way that is learnable from one stream of data and in a way that is composable. So by composability, I mean if the agent knows several things, can it quickly put them together in order to formulate a solution to a new problem, possibly in a zero-shot way? So in terms of procedural knowledge, one of the ways that I've been thinking about this for a long time is in terms of a particular framework called options. And one way to think about options is that there are controllers that start and stop. And so more formally, we think of an option as a policy that has an initiation set. It starts only in certain states. It has an internal way of choosing actions, and then it terminates possibly in a stochastic way, depending on the state of the environment. And so, for example, if you had a robot going around, its initiation set for a navigation option might be, is there anything in front of the robot? If there's nothing in front of the robot, then it can go forward, and it can go forward until it bumps into a wall or until it's too close to an obstacle. And so the way we think about the decision-making process is that the reinforcement learning agent now has decision points at which it can pick among these options. Options would be called, they execute, and then they terminate. And unlike in usual reinforcement learning, these decision points, which are sort of the circles in these pictures, the open circles, they are not evenly spaced in time, right? Because the robot only makes decisions at a time that an option has terminated. One of the interesting open questions is how would we decide what options are worth creating and worth keeping around? And so that's what we sometimes think of as a discovery problem. Now, in sort of industrial robotics, this is not left open. It's actually the designer of the system who builds controllers in a way that incorporates prior knowledge about the domain. But we would like these options to be acquired automatically from data, so the system should learn its sub-goals from data. And so there's been lots of heuristics and lots of thinking that's gone into this, what kinds of strategies we might use. I'm going to show you something really, really simple, which is actually automatic random generation. So this is work that we did a few years ago, where we simply allow the system to pick some random sub-goals, and then from the vicinity of these sub-goals, the system knows how to reach the sub-goals. So these are these little lily pads that you see in this navigation task. The system sort of sprinkles them around randomly, and from within each of these ellipsoids, it knows how to go to the center. And so we're comparing in this picture a system that just uses primitive actions with a system that sort of uses the lily pads. It's allowed to jump around. And what you see is that by introducing the structure, even though it has no prior knowledge really that's incorporated into it, we get a system that can achieve the goal. Not optimally, right? Because the knowledge that it decides on is actually pretty rudimentary, but it is able to achieve the goal, whereas a system that just uses primitive actions is still stuck in the corner because it's exploring randomly, and random exploration in this case just does not take you very far. There's a more sophisticated way of doing this, which is to say the system should have an optimization objective and then try to work with this optimization objective to create its sub-goals. And so this is an approach that we've pursued for a few years called option critic. And it's really inspired from this actor-critic architecture, which is a standard reinforcement learning architecture by Sutton and Bartow. In this case, you have an agent that has sort of two components, a policy and a value function. Not clear if this pointer is working. The policy is on the top, it chooses actions. The value function simply provides the policy with gradients in order to update the representation. And so we build an architecture that's very similar, but reflects the fact that the agent is now making choices among options. And so the policy structure on top is a little bit more complicated, has these slates that the agent can choose from. And the value function also needs to provide a little bit more signal because the policy structure is more complicated. So we have more information in the value function as well. This is work that's been published in 2017, and we have the code available online as well if you want details. So I just wanted to show you some results with this system. These are results in the Atari games that are often used for benchmarking reinforcement learning agents. And so what you see there, the horizontal red lines, are performance of the standard DQN agent that's used in these games. And the green line is option critic. And on the face of it, you think, well, why are you so excited about this, right? It just learns to be roughly on par with DQN. But the reason this is very exciting is that we're actually learning a lot more than just how to solve the task. We're learning a set of options that are potentially reusable in other tasks. We're learning a set of sub-goals and the predictions associated with these sub-goals as well. And doing this from the same amount of data as DQN is a win in the sense that we're acquiring more knowledge, leveraging the data in a better way. The other interesting thing on the bottom graph, you see some qualitative results from one particular game called Sequest. We're looking at what kinds of things are being learned, and actually this agent learns sort of two pieces of knowledge. One is that sometimes the submarine that is playing the game needs to go to the top of the water because it requires oxygen, and sometimes it needs to go down to pick up a diver. And so we can actually look at these agents and interpret a little bit better what it is that they do, and this is behavior that, again, is consistent in many of these games. Now, there is one problem with this approach, which is that in order to keep it very general, we allowed our agents still only to optimize the reward function of the task at hand and not anything else. And so as a result, they actually will acquire options, but then often if we let them run long enough, they will kind of dissolve them back into primitive actions. And that's because we know already from Markov decision process theory that optimal policies really can be expressed in terms of primitive actions. And so, in fact, this is the optimal behavior. But we, of course, would like to keep these options around because we believe that they would be useful later on. And so in order to do this, we use a framework, again, inspired from psychology theory called bounded rationality. The idea is that an agent would find it more difficult to make a choice than to just stick to whatever it was doing before. And so we penalize the agent for deliberating over its choices of option and hence encourage it to stick to an option once it's been chosen. And so this is an illustration of this approach in a game called Amidar. The farthest picture there shows what happens if you introduce no bounded rationality and no regularization. The agent basically just gets some very small pieces of behavior, but once you allow it to regularize using bounded rationality, you actually see the agent doing long trajectories that belong to each option and terminating in interesting places. So that where it tends to terminate is either around hallways where there is a choice of where to go, or in areas where there's an enemy that comes, and so you might need to terminate and switch direction. And so again, we see a little bit of interpretability emerging from these types of methods. Now, in this case, we basically introduce an extra term that is used to condition the termination of an option. And so there's a general question of, could this be done in other ways as well? And actually, we had a paper this year at AI Stats with collaborators from DeepMind, led by Anand Harutunian, which gives a general theorem that allows us to decouple the objective of the policy inside an option and the objective of the termination condition. And again, we can sort of look at the effect of this approach on some simple navigation tasks. And so what you see is if you use vanilla option critic, these options often will, in the end, terminate a little bit everywhere. Whereas if we encourage terminations to be focused only in specific states, we obtain this effect where the termination function is focused in just a few places, and performance tends to be better, although large-scale experiments are still ongoing with this. So this is sort of the procedural knowledge. We're going to think of it as being options. Now the question is, what kind of predictive knowledge do we want reinforcement learning agents to have? And so in order to do this the reinforcement learning way, we're going to think of the basic building block of predictive knowledge in this framework, which is the value function. And so there's a little bit of math on the slide, but it's actually interesting to think about it. What's the value function? The value function expresses an expectation, and the expectation is of a long-term quantity, which is the sum of rewards that the agent will receive over time. And typically, we also introduce a discount factor, which essentially tells us when the agent is going to continue and when it's going to terminate, right? And so we can think of this discount factor essentially as a continuation function, the probability that the agent will live and see another day. So the value function is a very general quantity in some ways. It is also somewhat limited in the sense that it is an expectation. It's not a full probability distribution, for example. But the advantage is that we understand it very well, and we've spent a lot of time, right, roughly 30 years, building very efficient methods for learning value functions from samples, doing bootstrapping algorithms, leveraging dynamic programming ideas in order to compute these effectively. And so what I'm going to propose to you is that in order to build predictive knowledge, we may actually consider a simple generalization of a value function that actually allows us to learn about many things. So we're going to generalize this in two ways. One is, instead of just thinking of numerical rewards and accumulating numerical rewards, we're going to think of general cumulants, which could actually, in fact, be vectors, or could be matrices, or could be tensors, okay? The only property that we require is, of course, additivity so that we can do the cumulative part. And so C in this equation is a general cumulant. As in usual reinforcement learning, we think of it as depending on the state and action and possibly the next state that the agent ends up in. The other ingredient here is going to be a slightly more general continuation function, which instead of being a fixed probability of the agent surviving at every time step is now going to become dependent on state. And so the agent is going to continue or to terminate depending on the state that it's arrived at. But the first work that actually proposed ideas of this type is very, very old. It's the pandemonium architecture, which was proposed by Oliver Selfridge back at the beginning days of AI in the 50s and 60s. And his idea was basically that you can have one stream of data, but an AI agent will have a bunch of little demons in its head that are all looking at the data and predicting different things and shouting out their predictions. And there will be a controller on top that listens to all these predictions and then decides what to do. And so this, in some sense, is an implementation of this idea. We're going to have one stream of data. We're going to have many different value functions sitting on top of the stream of data, computing expectations for very different cumulants, for different time scales. And all of these predictions will be available at the same time for an agent who tries to leverage them. And so we had an incarnation of this architecture back in 2011. And the ideas that we're looking at now are essentially extensions of this architecture. Now, one way to think about these value functions is that they're almost like little Lego building blocks of knowledge, where you have cumulants coming in, you have predictions going out, you have continuation functions coming in, and so you can start thinking of taking these value functions and hooking them up together, right, where, for example, a cumulant could be actually the output of a different value function, or our value function could be provided in features for a different value function. And so there's no longer the case that we have one value function inside the agent's head. In fact, we're going to have many. This is an idea that's also been explored in a more simplified form through auxiliary tasks in the work of Max Jaderberg. So there's actually lots of different things that can be expressed in this framework. And this is just a little laundry list for those of you who know about this: successor states and successor features, option models, feudal networks, value transport. So, you know, it's an interesting thing to think about this framework as being very, very general and expressive. Now the question is this just interesting conceptually, or can we do something with it? And so I'm just going to show you one potential use of this, which is actually illustrated in a NeurIPS paper that we have coming up. And this is the use of general value functions for synthesizing behaviors. And so the way we think about this is an agent might have multiple goals at different times. Okay, maybe sometimes it's hungry, sometimes it's thirsty, sometimes it's tired. Okay, so imagine this agent having at its disposal a keyboard, and each of the keys corresponds to a goal. And the more I press the key, the more the agent wants that goal. Now, you know, how do we decide what to do? Well, one way to think about it is the agent could play this keyboard one key at a time. One goal is active, the agent achieves that goal, then another goal is active, and so on. And that is the way that usual option execution would have worked, right? You pick an option, you stick to it until its completion, then you pick some other option. Now, if you're a musician, you know that it's much more interesting to do chords, right? So to play possibly multiple of these keys at the same time. Right? So an agent might be somewhat hungry and somewhat thirsty, right? And maybe it's not at all tired. And so that will create a new way of behaving. And so essentially what we do in this paper is we implement this idea by using linear combinations of cumulants, where cumulants can be positively weighted or negatively weighted, and the agent decides on the weights of this combination. And once the weights are there, because we've already learned how to achieve each cumulant independently, we have a single-shot way of synthesizing the behavior corresponding to it. And so once we're given a weighting of the cumulants, there's a general box that produces a policy that will achieve this particular weighting. And so this is just one simple illustration. There's an agent that's in a little round arena. It learns 3 different pure cumulants, which are going in these sort of 3 directions. But then if we place a goal anywhere arbitrarily randomly, the agent can figure out a weighting of these directions that will take it to that goal. And it can even learn to avoid a particular direction if necessary, because we're allowing negative weightings as well. And so what you see in the picture is the red curve is DDPG, which is a standard policy gradient primitive action algorithm. The green curve is Q-learning using the pre-trained options, and it achieves a certain level of behavior. But our approach, doing this kind of automated synthesis, is no more expensive, and it actually leads to better performance. So I'd just like to point out in the discussion that these reinforcement learning agents actually already have a lot of interesting ways of creating knowledge by using options and by using generalized value functions. And really a lot of the research going on right now is more having to do with the objectives that we should optimize while we are proposing cumulants, while we're proposing sort of the structure of the representation. There is, however, also one bigger open question which I would like to discuss, which is how do we actually want to evaluate empirically these agents? And when we are doing sort of pure reinforcement learning tasks like Go, that's actually fairly simple. There's a clear objective function, there's one reward, and we're trying to get the agents to maximize that expected reward. In the case of the agents that we're building now that have this kind of flexible knowledge, what we would like ideally is an agent that does continual or lifelong learning, that's in a situation where it interacts with the environment over a long period of time and keeps acquiring knowledge and using it. And so that is a much more difficult task to assess, okay? In some sense, we want to get at what does the agent know and what does it not know. And right now, the way we do this is by measuring its return, which is a very crude, right, single number kind of measurement of how well the agent is doing, and by looking at the qualitative behavior, which is interesting, but not always illuminating. Sometimes it's actually quite hard to qualitatively assess what these agents do. And so what I would like to point out is that perhaps as a field, we're going to need to rethink the way that we do empirical evaluation in order to gain more understanding of these agents. There used to be a time where we could do theoretical analysis and gain this understanding. Now these agents use deep nets. That's very hard to analyze theoretically. But from an empirical point of view, we may still want to sort of allow for an evaluation way that doesn't look at the return as the only measure, but actually tries to run targeted experiments where we make a hypothesis about what these agents might know, and then we run an experiment specifically to test if the agent has that kind of knowledge. And it's especially important when we are allowing the agent to learn this kind of predictive knowledge. So we might, for example, ask, does our agent know about object permanence? And in that case, we may run an experiment, which is a sequential task, to try and assess if that knowledge is present in our agent. So I really hope that in the long run, we will go to a method that is more like this, more like the scientific evaluation method. Thank you. I'll be happy to take questions.